Hello, how are you? In this video, we are going to define a just pure array of numbers, and then we're going to write to that just as we would an array of numbers, and then splat that to the screen as a texture. A reasonable question to ask would be, why do we want to do this? Well, it's true that OpenGL's standard polygon rasterization is a lot faster than this method. However, recently we've been doing raycasting, and raycasting involves drawing a bunch of lines. And if we invoke a vertex and fragment shader for every single line, that just gets too expensive. So just a little bit about the basic theory. So let's say we have a screen with some width and some height. We represent this screen with an array where OpenGL's texture coordinate system goes from the bottom left corner, where the bottom left is 0, 0, then across we have 1, 0, and the vertical goes from bottom to top. So the first few elements of the array would represent the bottom row of pixels, and then the next few would wrap around and address the second row of pixels, and so on and so on. So what we want to do is we want to repeatedly do this: draw a line like that. So to start with, to access the XY pixel of this element, we have the X coordinate plus the Y coordinate times the width, something like that, because this is our texture coordinate system, but really we've actually got numbers, so we'd actually have something like 240 across, and then 320 up, something like that. But there's a problem with this, and that is, okay, so let's say we want to write this pixel, and then this pixel, and then this pixel. We're not addressing adjacent memory locations, and that's a bit slower. You see, on a computer, when you access a random element of memory or an array or something, the CPU goes, oh damn, I haven't seen that before. So it doesn't just fetch that address, it fetches a bunch of addresses near that. And that makes, it caches those addresses, and that makes subsequent addressing operations a lot quicker. So if we can set this up so that as we slice across this wall, we're getting adjacent locations, then that's really good. So now we'll go with this system instead, and I'm going to exaggerate this just to make it clear which dimension is which. So we have a so we have a screen height and a screen width, but we've turned the whole thing on its side. And the reason we've done that is that when we go to draw a line, we are scanning directly across and accessing adjacent memory locations, which is more cache friendly and is a lot faster. So in this case, the index is the Y coordinate is going across from left to right, plus X times the height, because for every unit X we step across, we're skipping a whole H amount of pixels. So this will be a lot faster. And then the second thing, so the second thing I want to talk about is how do we actually store the color data for this. So remember, we're using red, green, blue, and alpha for each pixel, and it's tempting to make an array of these. However, Red is using 8 bits, 8 bits, 8 bits, 8 bits. So really, a 32-bit integer is perfectly fine. Now, if we look at a 32-bit integer, I'm just going to write in hexadecimal. So for example, if we had 255, that would be FF in hexadecimal. Red, green, blue, and alpha. So if I want to get a number which is 255 in the red and 0 in everything else, then what I do is I take the number 255 and I shift it to the left by 24 bytes. And then similarly, if I want to get the green amount into a number, well then I take my green number between 0 and 255 and I shift it to the left by 16 bytes. If I want to get my blue amount, take my blue amount, shift it to the left by 8 bytes, and I don't have to do anything to my alpha. So hopefully that makes sense. Let's actually jump into the code. First of all, we'll get a simple buffer system working, and then we will use it in our raycaster. Okay, let's get this started. So to start with, I guess we'll make a folder. It's basically what we're doing, CPU frame buffer. Okay. All right, cool. So let's start with the shaders. Okay, so basically what we're doing is we're taking a quadrilateral, we're plonking it on the screen. So I'll just paste this in. For some reason, it complains if we don't have this extension here. I think it's because we're passing data from one shader to the other. I think that's why we need it. It's just always needed this. Okay, so as we can see here, we take in a position and texture coordinate. We use the position to set our position internally, and then we use the texture coordinate, pass it along to the fragment shader. Okay, so then within the fragment shader, it's the same sort of stuff. We take in the texture coordinate, we have a single texture, and we sample from that texture and write it to the screen. So again, if you've done textured stuff in OpenGL, it's pretty standard. So let's make one. I'm going to call this is just a simple example to get it working. Okay. This will be very similar to what we had before in the raycasting example. So I'll just do all of my imports, just everything we would need. Now we need C types because we're going to be passing data over. Okay, so I'll just grab the class from before. Okay. All right. So just a few things. We just initialize our screen height and width. We store the clear color. Now, let me just do this. Let me make the clear color all red. So this is how we'll test whether our frame buffer is working, because we'll try to draw something on top of the red. And if we see red, we know that we're failing. I'm using red, green, blue alpha, so I want to possibly use blending operations, so I enable them down here. I create the shader, that's fine. And then I'm going to have two functions, one to create the vertices and everything for the quad, which is going to be drawn over the screen. And the other one is going to initialize the custom frame buffer. Okay. So that's the initialization. Let me just grab the create shader code from before. There we have it. Okay. Now for the new stuff. So first of all, creating the quad. So quadrilateral has, two triangles. So that's what we've defined here. Just note that the texture coordinates are a little bit messed up. Remember I was saying 0, 0 should be the bottom left? Well, I've changed the texture coordinates because what we're doing is we're referencing a texture which is like the wrong way up, right? So on my texture, if I draw this out, 0, 0 is the bottom left corner of the rotated texture. Draw this out on a diagram and then spinning it around 90 degrees clockwise. This is the layout. Okay. So yep, enable the arrays and attributes and everything. So the first attribute here is the position. Second attribute is the texture coordinate. That's fine. Okay, next thing we want to do is create the color buffer. Okay, so the color buffer is an array of raw data. So remember what I was saying before. This is a little bit wrong, isn't it? So 24 bits, that's the red bit. This is the green bit, the blue bit, and then the alpha doesn't need to be shifted. So what this is doing is just setting, this is a white color basically. We're going to experiment with this and get it, we don't need that. Okay, so we generate a texture, we bind it, we set a few bits of info. Usually with a frame buffer, we don't need to sample it. Even though we're not sampling from this frame buffer, we still need to set in like these parameters, like the minifying, magnifying, filter, and stuff like that. Okay, then we copy in the data. So this is allocating the data. Now note that we're not going width height, we're going height width. That's because the texture is spun around. And then we're specifying that we're using unsigned integers, 8 bits per component. And then we take the color buffer and we cast it to bytes, and that passes it in just fine. Actually, I don't know if we need C types. Maybe we don't. Let's see if we can get away with not using it. No, sorry, we do, because we're doing void pointer down here. Okay, that's fine. All right, so now let's keep going. So let's draw the scene, and we'll keep it really simple for now. Okay, so what do? We clear the screen. Again, that will clear it to all red. Then I'm going to call another function called clear screen where we pass in our own color. This will be like a really simple test just to check that it's working. Actually, let's not do that yet. Okay, now I'm going to grab this Pygame display flip and actually put that in the update screen. That's where I meant for it to be originally. Okay, so what this does is it passes in the data that's currently in the frame buffer, because this will potentially be changing every single frame. We need to pass it in all the time, and then just draw everything. Okay, so now let's create just a kind of a runner. So this is just using the same basic skeleton as in previous videos. So we set up screen width, screen height, we create everything. And again, I was doing this bit here just to log some debug info, but we can just run it. Okay, now we don't have players or anything, so we don't do anything in the handle keys, but that's all we do. So let's just run this and check that it's working. Oh no. Oh, I think I've got it. Sorry about that. So we created a shader, but of course, why didn't I catch that? We need to return the shader. It happens. Okay, so we've got this right now. It's just red. So we're goofing up somewhere. Okay, got that working. I think just something was unsaved. I don't know why. Anyway, so let me just check that again. So again, we create our color buffer. We've currently got 255 loaded in everywhere. Now, fingers crossed, because it took me so much to get this working. Okay, so if we... Okay, cool. Even if we're clearing the screen, it's not red, it's showing up as white. Okay, now let's make this partially transparent. Let's make it half transparency. And some of the layer below is coming through. If we make it 0 transparency, then yeah, okay, it's all red. That's good. That's what we expect. Okay, now let's just check that we've got our colors right. So this is red and blue, so now we should just be seeing pure green. Yep, that's good. And now like a cyan, like a mixture of green and blue. Awesome, awesome. Okay, so that looks like it's working fine. Now I want to show you the power of NumPy. So let's say we have a function called self.clearScreen. Screen is a set of pixels, so we'll go for pixel in not the actual thing, maybe something like this. Let's see if we can get this working. There, look at that. That is so slow. What, 4 frames per second? I thought this was fast. Well, have a look at this. Okay, so this is looping through kind of by hand. Now let's not do that. If we take, instead of accessing individual elements, and we just call this operator on the whole array, then under the hood, NumPy calls a, I think it's a C or a Fortran library or something to loop through its internal elements. Doesn't matter what the actual implementation is. The point is we get the speed of an optimized compiled library. And now we're running at about 25, so from 4 frames per second up to 2500 frames per second. That's good. Okay, so let's start doing things. So one thing we want to do is we want to be able to set the value of a pixel. Okay, so again, I actually don't need to do this, right? Self screen height. Okay, so we take in a color and we access the corresponding pixel and set it to that color. So let's test that. So what this is doing is setting the center pixel to blue. A little hard to see, but that's the pixel. True story. I spent 2 or 3 hours last night debugging this code just to get that blue pixel on the center of the screen. Now it turns out the mistake that I made is I copy pasted this code here, and I just got rid of the vertex position. So down here I was putting out to location 1, I think, and then over here I was taking in location 0 or something. Like it was a cross wire between my shaders, which is incredibly hard to catch when you're trying to debug this code over here. Anyway, the next thing we want to do, because we don't really care about pixels, I mean that's fine, but it's also very slow if we want to address the whole screen. So instead let's make a function which addresses a vertical line. Okay, and I will uncomment this. So what we take is if so height is really, because for our raycaster we know that our lines will be centered at the center of the screen, we have half of our screen height, half should be, the height above and below the center of the screen. It's basically what I'm saying. So what we do here is if that goes beyond the bounds of our screen, just constrain it. And I'll use that here and here. It shouldn't make an issue because we're just drawing a line with a height of 20 above and below. Okay, so remember our addressing scheme. So we have the center minus the line height. So if we're on, x equals 0, then this stuff doesn't matter. And our left address, if we're writing all the way to the top of the screen, will be, index equals 0. Then our right address will be halfway plus another halfway. So that's, index equals 240, the height of the screen, if that even makes sense. Okay, so we've basically got our indices, then we do a slice and we address that all in one call. And again, NumPy is incredibly fast at doing this. So here we have it, and we're drawing a set across the whole screen, and it's running at about 1400 frames per second. So again, that's encouraging. Cool. So then the question is, how do we use this in a raycaster? Well, let me just skip ahead. I'll make a new file. Something like that. And I'm actually going to just straight up copy all this code, put it over. Bada bing, bada boom. All right. So just go through this. We have the player. That's fine. This is exactly the same raycaster as before. I've just updated the drawing stuff. So the engine, again, we set things up. Yep, frame buffer vertex, frame buffer fragment. We create our quad and our color buffer, and then in self.colors we just do that bit shift operation to define a bunch of colors instead of using floating point descriptions. Okay. Yeah, create quad. This is exactly the same. Create color buffer. It's exactly the same. I've just copy pasted the code over. Yep, this is the same. Draw scene. Okay, so we go ahead, we do our ray tracing, and then right down the bottom, we just call draw vertical line. The X position is the ray index, how far we are, to the left or right of the screen. And that's good because ray index is automatically an integer, right? Height is, again, if our player is a distance of 1 from a wall, then we want the wall to fill the whole screen, I guess. So we just take the standard height, half... Oh, what am I doing? Okay, we'll see how that goes. Maybe I stuffed it, who knows. Okay, so we divide by the distance. Okay, and then to get the colors, instead of red, green, blue, I've just defined them up above with the bit shift, so we can just pass the color in directly as a number. Okay, that's fine. Yeah, clear screen, that's fine. Also, I defined this number here just to be like a slightly blue color, because I am actually using the clear value in this case. So again, this is the same vertical line code and the same update code. Oh, and another thing, why did I forget this? For the destroy, we should really be freeing the color buffer as well. So I'll just call this one here. Yeah, delete the texture, which is a color buffer. Okay. Now look at that. We are, at a 640 by 480 resolution, running at about more than 150 frames per second. And this is the important thing. Remember over here, this was about the worst case. So before we were optimizing, and our worst case we were getting down to about 70 or 80 frames per second. Now our worst case is about 130. And the cool thing about that is that there's not that much difference between the best case and the worst case. So we've improved our average case, I would say, and we've made it more stable. So yeah, that's fun. That's an example of using the CPU to control a frame buffer and then doing the calculation and then splatting that frame onto the screen in a single draw call. Hope you had fun. I'll edit this down. It's a little bit rambly. And yeah, see you next time. Bye.